Hello everyone, thank you for coming to the first theory lunch of the semester. Today we have Noah who will be talking to us about direct product testing.
Yeah, sure, thanks Andreas. Yeah, so the title of my talk is on the slide. It's about some stuff called direct product testers and also PCPs and also coset complexes. And I think most people in the audience probably know what at most one of these three things are. So I'm going to try to explain a little bit what these things are and what they have to do with each other. And also, feel free to stop me for questions or give me any feedback because I'm going to give this talk several times in the next month. Let me know if you have any thoughts. Okay, so the main goal of the work that I'm going to talk about, which is joined with my advisor Ryan, who's over there, is constructing these objects called direct product testers. Specifically, we want to construct great direct product testers. And given alternative construction, there are already great direct product testers, but we want to give an alternative construction. And great in this case means two things. They have to be sparse and they also have to have some good soundness property. And these two things, unless you know what direct product testing means, certainly don't make sense. So you can just ignore it and think of it as great. Okay? And these great direct product testers are known to be implied via some works that came out a few years ago by some other great type of object, which you also may not be familiar with, called a high dimensional expander, HDX. And I'm going to tell you what some of these things mean. And so after this implication was known, there were two works that were in parallel. I guess these two works were also in parallel that actually constructed these objects called great high dimensional expanders. They used a certain construction that was due to these people named Chapman and Lubotsky. And following up on this construction of great HDXs and therefore great direct product testers, there was another work which actually won the best paper award I think at STOC last year, which gave great probabilistically checkable proofs, which is another type of object that people are interested in. And that has some actual applications. In particular, they proved some new complexity results about hardness of approximation, I think exponential time hypothesis, hardness of approximation, and things like that. This is the history of this sort of area that we're interested in. I guess this is the recent history. There's been also a lot of works on these problems for many years. So the particular thing we're interested in is plugging in a new object here, a new HDX that gives a new direct product tester and a new probabilistically checkable proof that has some slightly nicer properties. So does that make sense as the general setup? Okay. So in particular, this Chapman-Lubotsky construction, here's a paragraph from a paper, okay, about this construction. And the thing that I want you to take away from this paragraph is the same thing that I took away from this paragraph, which is that I do not understand it. Maybe there definitely are some people who understand it, but I think that there are more mathematicians than maybe some theoretical computer scientists. Okay, there probably exist theoretical computer scientists who understand it, but maybe not very many of them. And yeah, it requires some knowledge of algebraic group theory and some other things that I at least personally don't know about. So this is my confusion mean. I don't understand what this construction is. Okay. So in particular, in this paper with Ryan, we analyzed an alternative construction called the Kaufman Oppenheim complex. So sorry for all the names, but there's the one we do is called Kaufman Oppenheim, or KO, and the one that was previously studied was Chapman-Lubotsky, or CL. And some nice properties that this complex has are that, firstly, it is elementary to define, and I'm going to tell you the definition in this talk. And secondly, there are some technical properties, like it's regular, so every vertex sort of looks locally the same. Also, it's very explicit, so there's sort of a formula for writing down the complex that works in a very sort of local way. If you ask what does the complex look like at some particular point, there's a super efficient algorithm to write that down. So there's some nice technical properties that this has. And the main theorem of our work is that these properties, which were previously known for this Chapman-Lubotsky complex, are also hold for this Kaufman Oppenheim complex. Okay, does this make sense? And yeah, so the main structure of this talk is as follows. First, I'm just going to tell you about a problem in group theory and how we solve it. Okay? After telling you about this problem, I'm going to tell you what this Kaufman Oppenheim complex is and what this group theory problem has to do with analyzing the expansion properties of this complex. And then at the end, I can tell you also a little bit about direct product testing and PCPs. Although actually, in our work, we just use some black box implications that if you get great enough HDXs, you also get these direct product testing and PCP results. So I'm going to emphasize that a little bit less. Okay. So first, I'm just going to tell you about some results in group theory, some older results, and then our new results. And I think the older results, I think we also maybe have a slightly different perspective. At least we're going to present it in a slightly different way than was already known. In particular, we're going to draw these pictures of circuits, which maybe are friendlier to computer scientists. So okay, so I'm going to start by just telling you about some model of circuits. So here's the model. There's some wires. Fix a field. So the wires at all points in time are going to carry an element from this fixed field, which like in our work is usually a finite field, but if you would prefer, you can also think of it as like the real numbers or whatever your favorite field is. And yeah, so at all points in time, every wire is going to contain a field element. And then there are these gates. And what do these gates do? So for instance, this first gate, you see this plus F gate? So this first gate, what it says is take whatever field element is currently in wire 0, multiply it by F, which is another field element, and then add the result onto the current value of wire 1. Okay? And if you prefer, you can also think of this as like a program. You can think of these wires like as registers, each register containing a field element. And each instruction says, for instance, the first gate corresponds to the instruction, take register 0, multiply it by F, and then add the result onto register 1. Okay? The reason I call these ordered circuits is just that I always require that whatever wire you're adding from is higher, or like a smaller number, but higher in the picture than whatever wire you're adding to. And I typically label the wires 0 through n, so there are n plus 1 wires, in this case n equals 2. And yeah, I guess I typically call whatever the wire you're adding from as is the head, and whatever wire you're adding to is the tail, and then the multiplier that you use is the weight. So the action of one gate is to take whatever value is currently in the head wire, multiply it by the weight, and then add the result onto the tail wire. Does this make sense as a model? Yeah?
But to confirm, we're reading time left to right?
Yeah, left to right.
Okay.
Yeah. So maybe this is like the quantum convention. Is that true? Yeah, so maybe, yeah. Okay, so one thing I want to point out about these circuits is that if I give you a circuit, the functionality of the circuit, meaning the mapping that says like given particular inputs, what are the outputs, is linear. That's just because each of these gates is like a linear operation. Okay? So for instance, if you like scale all the input wires by some scalar, then that also scales all the output wires by the same scalar. And therefore, we can always think of the functionality of one of these circuits as a linear map from n plus 1 wires to n plus 1 wires. And two circuits are going to be equivalent if they have the same functionality. So let's say I have one circuit, I have two circuits. If for every setting of all the field elements on the input wires, I get the same field elements on the output wires, I'm going to say these two circuits are equivalent. Okay? And I'm going to give you an example of what this equivalence means on the next slide. But for now, I'm also going to say that a circuit is trivial if it's equivalent to the empty circuit. And it's easy to check that that is the same as saying that the functionality of the circuit is the identity, meaning that anytime I put in some field elements on the input wires, I get the same field elements back on the output wires. Okay? And the group theory problem we're interested in is certifying triviality in a certain sense, and I'm going to explain what that sense is. Okay, does this make sense? Okay, yeah, please stop me if you have any questions. Okay, so here's an example of two circuits that are equivalent. So consider the following circuit with 4 gates, 3 wires and 4 gates. So I'm going to trace out what this circuit does on a particular set of inputs. So suppose I put in 3 field elements, V0, V1, V2. This first circuit takes V1 and multiplies it, so the first gate takes V0, multiplies it by F, and adds the result onto V1. So now the new contents of wire 1 is V1 plus F V0. I multiply this by G and add it on, I get this. Then I take V0 and I multiply it by minus F, and then, so I'm basically subtracting F times V0 off of this value, so I get back V1. And I subtract G times V1 off of this value, and I just get V2 plus F times G times V0. Okay? So can anybody tell me what this circuit is equivalent to? The circuit I wrote in the top left? Yeah.
Just one wire from 0 to
Yeah, exactly.
F2.
Yeah, one gate. I don't know, the terminology is like slightly made up anyhow, so it's not that important, but yeah, so if I just have a one gate circuit that just takes the contents of wire 0, multiplies it by F times G, and then adds the result onto wire 2, these two circuits are equivalent, even though they look different. Like that's a 4-gate circuit, this is a 1-gate circuit. Okay, so somehow equivalence of two circuits is actually, can be, I mean, in this case it's pretty easy to see. You can always test by just doing this linear algebra out, but in general there can be sort of complicated reasons why two circuits are equivalent. It's not always completely clear. Okay. So now I'm going to talk about what I mean when I talk about certifying triviality or equivalence of circuits, okay? So I'm going to make a slightly artificial definition, and this definition I'm just going to make because it is the right definition for a problem, and maybe you'll be convinced later in the talk why this is the right definition, but for now take it on faith that this is like an interesting problem. So, okay, I have n plus 1 wires. I'm going to just pick 3 gaps between 2 adjacent wires, and I'm going to call them modes. Okay, this is the use of the word moat, like a moat around a castle that you can't cross, because we wanted something that represents something that you aren't supposed to cross. Okay, so in particular, here's an example. Here's like a circuit, and I shaded the gap between wires 0 and 1, the gap between wires 1 and 2, and the gap between wires 2 and 3 by different colors, and those are going to be the 3 moats. This is the minimal example, but we can also consider 3 moats in having more than 4 wires, but you need at least 4 wires. Okay? And what I'm going to say is that a region of a circuit is a contiguous subcircuit, meaning like some adjacent gates in the circuit that all do not cross the same moat. Okay? Here's an example. So see this F gate and the P gate? Okay, they both don't cross this 3rd moat, which is shaded purple if you can see the purple. So because these two both don't cross the same moat, I say they're a region. Okay? And the allowed operation is the following. You can take a single region, in this case the purple region consisting of the F and P gates, and replace it with another region, which is equivalent, meaning it computes the same function, has the same functionality, but this new region also has to avoid the same moat. Okay, so for instance, you can see that this F gate and this P gate commute. That's because they both just read from the same input wire and their outputs don't interfere with their inputs. So for example, I can do this local transformation where I just swap those 2 gates. That's allowed because none of these gates are crossing this purple moat, so this is an allowed operation. Okay, does this make sense? Okay, so now I'm going to claim that whether you can reduce a circuit to the identity using local transformations is actually very non-trivial. And actually, it's maybe in general, in the most general versions of this problem where you allow more complicated gates, is undecidable. It's called like the word problem in group theory, if you know about that. So here's an example. I'm not going to show you like the entire proof in detail, but it's just sort of more to prove a point. Like look at this circuit, okay? Here are 4 gates. This circuit is trivial. And that's just because these 2 P gates labeled by plus P and minus P are like operating on disjoint sets of wires in the 2 Q gates that are labeled plus Q and minus Q. So like really you can slide this Q plus Q past the minus P and they'll cancel each other out. So somehow this is a trivial circuit, but the triviality of this circuit is not really captured immediately by a local transformation because like collectively these gates cross all the moats. So you can't just be like, I'm going to collapse this to the empty circuit in a single operation because there's no moat that sort of allows you to do that. Okay? And so in particular, the sorts of things you can do, I'm just going to show you a simplified proof that Ryan, I think, found after a lot of maybe work on a piece of pen and paper. There was an earlier proof that was known that was a little more complicated. Does things like the following. You like take some of the gates and you like expand them out in these like weird ways where like you in particular note that there's like a half appearing, so this half only makes sense when the characteristic of the field is not 2. But assuming it's not 2, you can do some like weird things, and at every step you're just like, oh, I'm going to look at some adjacent gates that don't cross a moat and replace them by equivalent adjacent gates that also don't cross the same moat. So when you do a bunch of these steps and like, ta-da, you actually can reduce to the empty circuit, but that was kind of hard in the sense that this proof took us a long time to find and also doesn't seem to generalize well to some other settings. Okay, but in this n equals 3 setting, these authors named Vyas and Dasgupta, who also proved the triviality in local transformations of the circuit on the previous slide, proved the following theorem, and I think this was in like a Journal of Algebra paper. So firstly, I'm just going to say, whenever we're talking about certifying a circuit using these local transformations, we're always going to assume that the circuit that we started out with has the property that all gates do not cross all 3 modes. Yeah?
Like, isn't certifying triviality not that hard? Like, these are all matrices. So
yes, but the question is whether you can certify it using only local operations, like I put on the previous slide.
But like multiplying matrices that are next to each other is local, right?
Yes, but it's like this is true, but the question is, like if you start out with a circuit, this is a good question. You start out with a circuit like this, so this circuit is trivial, but it's not clear whether or not it is possible to certify the triviality using only these local transformations. Because like if you look at this, I mean I guess like it is true that when you multiply these corresponding matrices together you get the identity matrix. Yeah. But for instance, even if like the field had characteristic 2, this would still be true, but there's counterexamples that show that you cannot certify triviality using only local transformations.
What is a local transformation?
It's literally like, if you want to think about it in terms of matrices, there's like certain subgroups that are defined as like using only certain entries in the matrices, and then you're only allowed to apply operations that fall within these different subgroups. So it's like a limited proof system.
Sorry, maybe you should just re-show the slide with definition.
Oh yeah, I can go back again. Yeah, so you're allowed to look at adjacent gates and replace them by equivalent adjacent gates, but the adjacent gates all have to lie within the same, like all have to not cross the same mode.
Some kind of like memory issue. Can't track.
I would think of it more almost, at least the way I think of it is like as almost like a rewriting system from like a formal languages perspective or something. Or like it's like a proof complexity problem. Like the statement is true, but the question is, can you prove it in some like weak proof system? And in fact, we know that if the characteristic of the field is not 2, you cannot, is 2, you cannot prove it in this weak proof system. Yeah. Okay. It's like a question about whether these local operations are enough to capture all true linear algebraic facts that hold about these operations. So it's like, it's more of a question about whether locality captures the entire sort of matrix type computations that you were asking about.
Yeah.
Okay. Okay, so as I said, there's this weird stuff that happens when the characteristic of the field is 2. But ignoring that, okay, so first when I talk about certifying these circuits, I'm going to say that I'm just going to ignore gates that cross all 3 wires. That's just because if I have a gate that crosses all 3 wires, then these local transformations can't even do anything to this gate, because they only work on gates, sorry, I shouldn't say cross wires, I should say cross modes. So, sorry, I'm going to assume that there's no gates that cross all 3 modes, because if there is, then the local transformation can't do anything about it. They can only operate on gates that avoid at least one of the 3 modes, okay? And so assume I'm always now talking about such circuits. So this and Dasgupta showed that if I have 4 wires, which is the simplest possible case, and I start out with a circuit that has constant length, and also the characteristic of the field is not 2, then I can certify the triviality using local operations, and here using a constant number of local operations. And by constant, I mean that, that this constant is independent of the field f. In particular, if f is like a finite field, this means it's independent of the size of the finite field. But it also would work for real numbers or complex numbers or whatever. Yeah, so like this theorem includes as a special case this magical derivation I showed you a few slides ago. Because that's one example of a constant length circuit that is trivial, so you can indeed certify it's trivial. Yeah, this is a picture Ryan found of Biss and Dasgupta when they were still PhD students. And like a funny bit of math history is that Daniel Biss, the guy on the bottom, is now the mayor of Evanston, Illinois, where Northwestern University is, and he's currently running for Congress, which I think is kind of funny. It's the first mathematician I've ever cited who's currently running for Congress. Okay, so unfortunately, the model that we actually have to study in our paper is slightly more complicated than the model I told you about. So I'm going to tell you about this complication, and I'm going to mostly ignore this complication for the rest of the talk. So the complication is that in our actual model, instead of just carrying field elements, the wires are going to actually carry polynomials, where like the coefficients are in the field, okay? And again, the gates have like a head and a tail and a weight, but the weight now is a polynomial that has to satisfy a particular restriction, which is that the degree of the polynomial has to be at most the height of the gate, which is just the difference between the head and the tail, like the number of wires spanned by the gate. Okay, this is like again, I'll tell you maybe a little bit more later about why this is the right model to consider, but I'm just going to tell you that this, for now, is the right model to consider. And Kaufman and Oppenheim a few years ago proved an analogous theorem to this Biss-Dasgupta theorem that I had on a previous slide, where instead of just working with these normal circuits, they work with the graded circuits, and they can certify all constant length trivial circuits using constant number of local transformations. Yeah, Henry?
What does the restriction mean? Like, does it mean we're restricting to inputs where this would be true?
No.
Or it doesn't, the gate just doesn't work if it...
Like, I'm now going to, but maybe it's confusing because inputs, you can think of the inputs as being polynomials of any degree, meaning inputs like the inputs to the wires, but I'm now restricting the types of operations that the gates, like the types of gates that you're allowed to use.
So you're not...
So you can't do like you can't add an arbitrary polynomial multiple of wire 0 to wire 1. You can only add a linear polynomial multiple of wire 0 to wire 1.
I see.
Yeah.
So it's only in there.
Yeah, exactly. So maybe a clarification here, which I had also, is that, okay, for example, consider the following gate. This is a gate that adds a p times the contents of wire 0 onto wire 2. Okay, so in the field element setting, p could just be a field element, but now p is supposed to be a polynomial. And in particular, since this is a height 2 gate, p is supposed to be restricted to be like a quadratic polynomial, because like 2 minus 0 is 2. So somehow, in the original setting, we would have wanted to say things when we're doing these calculations like, oh, I don't know, you expand this one gate as like this subcircuit of 4 gates. That's like the calculation that I showed you towards the beginning. But somehow now this is not actually allowed because p is quadratic and here p has to be linear. So you have to do annoying things like split p up based into different linear and constant and quadratic terms. And okay, anyhow, this is sort of a headache when you have to actually do the grading, and so we're mostly going to ignore it and think just about the normal model. Yeah.
Why? I just think I'm talking about like O of 1 local transformations. Like you said before, if characteristic is 2, you can't even necessarily certify it's trivial using local transformations, right?
Yeah, but the point is that for every field where the characteristic is not 2, like there's a constant independent of the field that works for every field that does not have characteristic 2.
Yeah.
Yeah.
And you can do it, but like this is a new thing, right? Like before you were just talking about whether it could be certified. Now we're talking about like you can certify something like efficiently.
Yeah, this is true. Although I think somehow it is new, but somehow like it doesn't. Maybe it's like slightly misleading to write this O of 1 just because, like, for example, if you go a few slides back and like this proof that I did, like the point is that this proof, like it doesn't. Nothing in this proof depended on the field except that the field has an element called 1/2, like 2 has a multiplicative inverse in the field. So like somehow the O of 1 is just capturing that I can completely ignore the field in this proof aside from that 2 has a multiplicative inverse. Yeah.
But does it depend on the input size?
You mean the size of the circuit?
Yeah.
Yes.
Okay.
Yeah. And yeah, I'm going to say a little bit more about this.
So O of 1 because n equals 3.
Yeah. Oh, this is a great point. So this is like a very good point. So in particular, the actual problem that we're interested in, which Henry is sort of getting at anyhow, is that we're interested in the problem where n is now a growing parameter. So in the previous examples I showed you, n has always been 3, so there have always been 4 wires. Now we're thinking of n as a growing parameter. And we're going to make one additional assumption, which is that these motes, which have gaps in between them, the gaps are not too small. And I'm going to also show you, I think on the next slide, why this is a useful assumption to make. But we're going to assume, say there's like n wires or n plus 1 wires, that the gaps between the motes are like, I don't know, 0.0001 times n wires wide. So they're not too small. I'll show you a little bit about why this is useful. And yeah, so the theorem that we prove in this setting is if we start out with a circuit, the circuit is trivial, and it has constant length, but this is length in a slightly weird metric that I'm going to call region length, and I'm going to tell you what that is in a sec. Then the circuit can again be certified using a constant number of local transformations. And again, sorry, I shouldn't say again. So in response to what Henry said, we're now thinking about O of 1 as this constant as meaning not just independent of the field F, but also independent of n, which is the number of wires. And that's what is important for our application. So we're interested in getting these certificates when you start out with a circuit that has a constant length, and we want the number of steps you need to do to be independent of the number of wires. But when I talk about this length, and this is sort of the key point, when I say region length, I don't just mean the number of gates, I mean the minimum number of regions that the circuit can be partitioned into. So if you can take a circuit and partition it into a constant number of regions, then I'm going to still say this is a constant length circuit. Okay, so this is a slightly different definition of length than I was giving on the previous slide. In particular, like a single region can have n squared gates in it, because like let's say the mote is in the middle, and like all gates that are just above the mote, there's like n squared over 4 of them or something, and then n squared over 4 below. So there's like many possible gates that are appearing in each region. So now I'm interested in doing things like certifying a circuit that has like quadratically many in n gates. Maybe so it's a constant times n squared number of gates, and I want to certify this entire thing all the way down to the empty circuit using just a constant number of these local transformations. But each local transformation could potentially work on a quadratic number n squared many gates at once. So this is the sort of game that you have to start playing. Okay, does this make sense? Yeah, ask me if you have any questions. Yeah, so basically how okay, maybe first I'm gonna say,
You have another question?
yeah, oh, sorry, I missed
Wait,
it.
formally, what is region then? The minimum number of regions?
Yeah, like the minimum number.
But this is not something you get for free for n equals 3, right? Or is it? Like,
I think it's basically the same. I can say a little bit about why it's basically the same.
okay.
So like every region you can sort of, maybe I'll answer this question later. It'll be a little bit
Sounds
later.
good.
Okay. So now I want to just give a little bit of intuition about why we have this condition that says that there's some distance between the modes and why this might be helpful. So the intuition I want to give is the following. This is a similar example to the example I showed you before where we had some P and some Q and we want to commute them past each other, okay? And again, you can't do this whole thing in a single local transformation because collectively these gates all cross all three of the modes. But somehow now this problem, now that we have more wires between the modes, this problem becomes easier. So in particular, you can just sort of expand the, you can expand these gates in such a way that like the expansions all use disjoint sets of wires. So like this Q I expanded into these 4 gates, and that P I expanded into 4 gates, but now like the wires that are being used by like this 4-gate subcircuit and the wires that are being used by this 4-gate subcircuit are disjoint. And that means everything just sort of slides past each other. Okay, maybe this doesn't make sense, but I guess at least the intuition that we had is that somehow you can think of the wires that are occurring between the modes as some sort of temporary workspace or like scratch pad or something that you can use. And so having more space between the wires gives you more flexibility to sort of copy intermediate results into like your scratch pad in ways that don't interfere with other calculations that you're also doing at the same time. So you can sort of do more calculations in parallel. This is again the sort of consideration that goes into our actual proof. Yeah, so you just sort of slide, you can sort of slide things. Okay, and now maybe I'll say a little bit about how the actual proof of our theorem works. Okay. So here's a folklore lemma that is not very hard to prove. Okay, pick your favorite order of the gates. So there's head-tail pairs that describe the different gates. Pick your favorite ordering of these pairs. And the lemma says that every circuit is equivalent to a unique circuit when you order the gates in the specific way. So for instance, here are the 6 possible sort of shapes of gates for n equals 3. There's like 6 pairs of wires that you could pick. I've labeled them here as F, G, H, P, Q, and Z. And what the lemma says is that, for example, in this ordering, you can take any circuit and it has to be equivalent to a unique circuit of this shape, okay? So what this means is that if you want to certify the triviality of a circuit, it's sufficient to just put it into a normal form. Because if the circuit starts out, if the circuit is trivial and you put it into normal form, then all of these coefficients, F, G, H, P, Q, and Z have to be 0 by uniqueness. So somehow the problem we're trying to solve with certifying trivial circuits is the same as the problem of putting circuits into normal form. Okay, yeah?
So you could have multiple copies of each of these types of circuits,
Yes.
but you can rearrange it to this order, and then all the ones that are the same shape would collapse. So you really, okay.
That's exactly right. Yeah, and I'll tell you a little bit more about why this is true. So somehow the strategy that we want to implement is to normalize circuits using some sort of sorting operation to put the gates into the right order. And yeah, so like I'm not going to show you all the details. It's a little bit tedious, but basically, like if you have, say, like you have a circuit, it's not in the right order. You're like, I want to swap the +3 and the -2. So you like do something, and then it puts it in some order. But like maybe doing that creates a new gate because these 2 gates didn't commute. So like maybe you've now created a new gate. You have to like put that gate in the right order. But you basically do some bubble sorting operation where you can put the original gate, the original sequence of gates into the right order using only local transformations. Okay. And in particular, what this means is that in order to certify an arbitrary circuit, you actually need to only be able to sort of implement a pretty small set of operations using local transformations. And in particular, these operations are called Steinberg relations. And this is Robert Steinberg. I think this is also a picture Ryan found of it. Okay, so the first operation, this is exactly what Andrew was saying, is that if you have 2 adjacent gates that have the same shape, you can just collapse them into a single gate. Like if you add F1 times a certain wire onto another wire, and then you immediately just add F2 times the same wire onto the second wire, you could just think of it as doing one gate where the multiple is F1 plus F2, okay? And then also, if you have adjacent gates that use disjoint sets of wires, you can just slide them past each other. I guess also the case where I equals K or J equals L is also works here. And then finally, you have the case where there's some shared wire, like one of the output wires of one gate is the same as the input wire of the other gate. And then when you swap them, you create a new gate. And this is the same as the calculation that I was showing you a while back. So anyhow, exactly what these relations are is not so important, but the point is that if you can implement these operations by local transformations, then you can sort of use this to do some sort of bubble sort operation and use local transformations to put an arbitrary circuit into the correct order. Yeah, go ahead.
Are all of these types true only for graded circuits or for all
No,
circuits?
this is true for
all
everything.
circuits?
Yeah, good question. Yeah, so somehow the proof strategy is just to use these local operations, implement them via local transformations, and then put an arbitrary circuit into normal form. So for instance, like in the n equals 3 case, one of the relations says that you can swap a P and a Q of this form, but I already showed you a proof that was non-trivial, but the proof showed that you could implement this sort of swapping operation via local transformations. Okay, this was this magical proof that I showed you before. So again, some of these swapping Steinberg relations are already just immediately local transformations. Some of them are not local transformations, but they can be implemented via local transformations. Yeah, and like a technical point, which feel free to ignore if it doesn't make sense, is like there are some Steinberg swapping relations that involve gates which cross all three modes. This is annoying because this gate, it doesn't even make sense to talk about these sorts of gates using local transformations. And so somehow, like when you actually do this, you have to do tricks like encode, whenever you want to talk about a gate that crosses all three modes, talk about instead a subcircuit that doesn't cross all three modes but is equivalent. Okay, this is just annoying stuff that you have to actually do. Okay, so in the end, our proof looks something like the following. Again, the statement says if I have an arbitrary circuit and I want to certify that it's trivial, I can do it with a constant number of local operations, and in particular, the number of local operations is supposed to be independent of the number of wires. And that's what's like really important for the actual application that we need. And the proof strategy is roughly the following. We're going to take all these wires and we're going to group them into chunks. And in particular, we're going to do it in a way where like none of the chunks crosses a mode. So like we look at all the wires between each pair of modes, or between the top and the first mode, and group them into chunks. These chunks are going to be big, so each chunk is going to have order n wires in it. And then we're going to think of each chunk of wires, which is like a really thick bundle of wires, as actually an extremely thick single wire, where instead of carrying, having individual wires which are each carrying a polynomial, we think of it as one giant thick wire carrying a vector of polynomials, okay? And similarly, when we think of a gate, instead of thinking of a gate that operates on a single input wire and a single output wire, we think of a gate as operating on this thick bundle of input wires and a thick bundle of output wires. And somehow then the weight, instead of just being a single polynomial, it's like a matrix of polynomials. We do the Steinberg relations again using these matrices and vectors instead of just using single polynomials. Somehow everything works out if you do this strategy the right way, although it's very annoying because you have to take care of various edge cases and things like that. Yeah. Okay. Yeah. Maybe that's all I want to say about this. Okay. Any questions about this sort of problem? Yeah. Go ahead.
Roughly how big is the constant?
I think the constant. Okay. We do not try to optimize it. I think the thing that ends up being the most relevant is that you have to. So I think we call it in the paper. We thought of it as like the aspect ratio. Is a measure of exactly, so we said that the gap between the first mode and the second mode, and the gap between the second mode and the third mode have to be linear in n. Whatever that constant is the constant that actually determines the final O of 1 that we get. It's polynomial in that constant, but we didn't try to optimize it. I think it's a bad polynomial, like maybe it's like the reciprocal of the constant I just told you to like the 20th or 30th power or something like that. It's not horrible, but yeah. I mean, it's pretty bad, but it's not like a tower type dependency or exponential or something. Yeah. Yeah.
I'm assuming that we can do all of this only for graded circuits. So I was wondering, like, which point exactly can we not do for like ungraded?
No, we can do it for ungraded circuits. Graded circuits are kind of harder.
Oh.
Yeah. Sorry, maybe I should have said that more clearly. Yeah, like, for example, the grading just makes things actually more annoying. So like, for instance, this example that I showed before, wait, let me go find it, here. Like somehow when you do grading, you have to start worrying about like, oh, are the circuits I'm writing down legal? Because you have like, you have these extra constraints on like the degrees of the weights that you're using. So it actually makes things strictly more annoying. Yeah, I should have maybe said that more clearly. Okay, so now I'm in the remaining time, I think it's like 12:40, and maybe I'll try to take about 15 more minutes. I'm going to tell you about what this Kaufman Oppenheim complex is and what it has to do with this group theory I was telling you about. And then I'll tell you maybe a little bit about the applications that we end up sort of getting. So first I'm going to tell you a little of group theory that you need to understand this definition. So firstly, there's a definition of a coset, which you may have seen before in like a group theory class. If not, I'll tell you, if you have a group G and you have a subgroup H, then every element little g in this big group G determines a coset of H, okay? And this coset is written little g times H, and it's simply the set of all elements of the form little g times little h, where little h is in this subgroup big H. This is just a set of elements, that's a subset of the group. It's not a subgroup necessarily, but it's a subset of the group. The important facts about the cosets are the following. Firstly, the cosets partition the group. So the group can be written as like a disjoint union of cosets. And also, every element is a member of its own coset. So like if I look at little g, then little g is in the coset little g times big H. This is just because big H contains the identity element. Okay, and in this talk, I'm going to write the set of all cosets as G mod H, written like this. Okay. By the way, I say left cosets because you could also do right cosets where like you had big H times G, and the groups we're interested in are not necessarily abelian, so these could be different. Yeah. Okay. So in particular, we're interested in the following construction, which is what's used to do these Kaufman Oppenheim complexes. It's called a coset complex. Okay. A coset complex is defined by a group G and several subgroups. So label them, I don't know, H1 through HK. It's already interesting to think of the case where K equals 2 or K equals 3. And this coset complex is going to be a hypergraph. It's going to be a hypergraph where there are some vertices, and then every edge contains exactly K different vertices. Okay? In particular, this is going to be a part-type hypergraph, which means that the vertices can actually be divided into K different types, and every hyper edge contains exactly one vertex of each type. Okay? And I'm going to show you a picture of what this means in a second. So, okay, by the way, there's a technical assumption which you can ignore. So, there are K different types of vertices, and each type of vertices corresponds to cosets of one of these subgroups. So if I have 3 subgroups, then there are 3 different types of vertices, yeah?
I think we have the same question. How is the intersection empty of the subgroups?
No.
The identity element.
Sorry, the identity.
Okay.
Sorry, somehow this is, okay, good point. Somehow I think of it as being empty because in my head, like it's the minimum possible intersection, which is the same as what's happening in set theory. Like this is, the like some category theory going on.
Maybe the identity element is written with that same.
Yeah. This was actually like a really powerful move on my part. No, yeah, good point. Yeah. So now when I make hyperedges, I'm going to just look at every element little g in this big group big G, and then I'm going to place a hyperedge which contains the different cosets of this group with respect to all the K different subgroups. So somehow you should visualize this as something like this. So for example, this is the case where I have 3 different subgroups. And okay, so each of these cosets, each of these sets of cosets forms like a partition of the group. So I have like one partition of the group, and then I have another partition of the group, and then I have another partition of the group. And then for each one of these elements in the group, I'm going to create a triangle. And the triangle is just like, what is the coset with respect to this subgroup? What is the coset with respect to this subgroup? And what is the coset with respect to that subgroup? And I just plop down a triangle for the 3 corresponding cosets. Okay? Maybe you might not have any intuition for what this construction is, but maybe you can at least trust me that this is like a completely elementary construction that only uses some very basic finite group theory and no scary words like lattice, profinite, and so on. Okay, compact open subgroup. Okay, yeah. Also, this construction has been around for a long time. It's like, I think, maybe at least 75 years. Okay. So now I'm going to tell you about one of these actual coset complexes and what this has to do with all the group theory I was telling you about at the beginning of the talk. So fix n, which is like the number of wires, or the number of wires minus 1, and fix a field f, your favorite field, and also fix the positions m1, m2, m3 of the three modes. Okay? This defines a coset complex as follows. I'm going to call it the restricted KO complex. And we are the first, I guess, to explicitly study this complex, although it's sort of maybe you eventually understand that it's the right complex to study once you're sufficiently interested in the problem of proving direct product testing, testability of this of the big KO complex. Okay, so the group G that we're going to use is just basically the group of ordered circuits, which I was telling you about before, or specifically the group of functionalities of these circuits, but you can sort of forget the functionality thing. And so for instance, like in n equals 3 case, there's only 3 possible modes, and the complex is like all functionalities that can be written in this form, where you have like these different gates. And then there's some subgroups. So what are the subgroups? Just for each mode, look at what are all the functionalities of circuits that avoid that particular mode. So for example, in the n equals 3 case, you can look at the first mode, which is this TL1. You'd be like, what are all the different possible gates that avoid this mode? It's like these 3, and then, so these circuits of this form and the functionalities thereof form a subgroup of the bigger group, which is like all possible circuits on 4 wires. And similarly, you can make 2 other subgroups, which are like corresponding to the other modes. And then you literally plug these subgroups into the construction that I put on the previous page, and you get this 3 uniform 3-part hypergraph, which is called the restricted KO complex. Okay? And this is the goal of our work is to prove expansion, whatever that means. I'll say a little bit about what that means, of that restricted complex. And somehow this ultimately implies some stuff about direct product testing. Okay, so let's see. So the complex I told you about on the previous slide was like a rank 3 complex. There were 3 subgroups corresponding to the 3 modes. So this subgroup is related, this complex is related to a larger complex, which I'm going to call the local KO complex. It's very similar. The only difference is that instead of picking only 3 modes, I now look at all possible modes. So there are like n possible modes. This is a rank n complex because there are n different subgroups. And the complex I told you about in the previous slide is literally like you take this complex and then you restrict it to only 3 of the parts as opposed to all n of the different parts. Something like that. Okay, this is a complex that was definitely studied in previous works. And this complex, okay, this slide is going to be confusing, and I actually want to put some time into making a picture, but I haven't been able to make a good picture yet. But somehow the local KO complex I told you about in the previous slide is only a small part of an even bigger complex called the global KO complex. And this complex is weird because unlike the examples I was telling you about before, now we have to consider circuits where the gates can also go upwards instead of just downwards. Okay? And you might object that once you allow gates to go upwards, if you're in the graded setting where you have polynomials, then somehow you can now get polynomials of arbitrarily high degree. So there's like, this is now an infinite group of potential different functionalities. That's why we have to also have a irreducible polynomial and mod everything by an irreducible polynomial. But that's a technical thing you can kind of ignore. And basically we allow upwards and downwards gates, and then we have to have an appropriate definition of subgroups where now you can have modes, and you also have to have a mode between wire n and wire 0, which doesn't really make any sense in the picture I had before. So I think the figure that I wanted to draw at some point was something like you actually sort of view the wires as now sort of existing in like a cylindrical like bundle or something, and then the gates are sort of on the surface of the cylinder, and the modes are sort of between the sort of different the gaps between adjacent wires that are arranged in sort of a circle or something. Okay, and I guess I should say that for the expander heads out there, that somehow the choice of this irreducible polynomial in terms of letting it have higher and higher degree is what lets you go and actually define an infinite growing family of graphs, which you might care about if you wanted to design expanders, which is what we want to do. Okay. Feel free to ignore that if that doesn't make sense. Okay, and here's just like a diagram that I'm not going to try to explain, but I just want to like say some things qualitatively. In the end, the actual application of all of our group theory work is to prove some great HDX property about this global KO complex. What we actually prove is some expansion property about this restricted complex, which is the one that's the most similar to the group theory that I was telling you about before. There's some other conditions which you also need to throw in order to get this great HGX property, which you need for direct product testing. There's some relatively easy condition which we prove as a lemma, and then there's also this sort of completely different global condition which needed to be checked in this paper by Kaufman and Oppenheim and Weinberger, which is also complicated. So I think that in the end you should view, accurately, you should view this expansion properties of the global complex which get direct product testing as sort of a combination of this KOW paper from last year and then our new result, and then we do also all the gluing that puts everything together and gets direct product testing and PCPs. Yeah, and then maybe at the end, I'll say a little bit about what expansion means when you're talking about a coset complex. So again, the setup for a coset complex is you have a group and you have some subgroups. And we're going to consider words, and a word is just going to be a sequence of elements where each element is in one of the subgroups. And then we're going to consider some notion of local transformation on these words. And local transformation means things like take two elements that are in the same subgroup and replace them with their product, because the product also has to be in the same subgroup. Okay, I'm not going to be very careful about defining exactly what this means, but it's essentially analogous to the circuit operations that I was telling you about before with respect to local transformations. And a theorem which was proven by Kaufman and Oppenheim about 5 years ago, and then which we strengthened, and we need this sort of strengthening in our new paper, is that expansion of a coset complex means that you can do some sort of local certification of all words using local transformations. So I'm not going to be very precise about what this is, but it's basically the glue between the group theory that I was telling you about at the beginning of the talk, where we had these circuits and we're talking about how to locally certify them, and then some actual expansion properties of these objects, these sort of graph-like or hypergraph objects called coset complexes. Okay, and yeah, again, maybe if there's any group theory heads in the audience, there's this guy named Max Dane who studied this thing called the Dane function, and that is a measure of the complexity of certifying words via restricted types of transformations. So the thing which you actually end up needing to study is equivalent to or similar to these sorts of group theory considerations which have been studied for a while, but now in application to these specific groups that we care about. Okay, so I think I'm going to actually end it here. So I can say a little bit more depending on people's interest, or like after the talk or just now, about what the direct product testing problem is and what the application of our work is to direct product testing. But I think it's like 12:53, so if anyone has any questions they would rather ask, let's do that.